Today we are going to continue talking about Euler paths and circuits. We're going to start by looking at 3 theorems regarding Euler paths and circuits. First is the Euler circuit theorem. If a graph is connected and every vertex is even, then the graph has an Euler circuit, and it probably has more than one Euler circuit. However, if a graph has any odd vertices, then it does not have an Euler circuit. So let's take a look at these 3 graphs, decide if they have Euler circuits or not. So in our first graph, this graph is disconnected. So it does not have an Euler circuit. There is no possible way that we can trace the whole diagram without picking up our pencil. The second graph is connected, so now we need to look at the degrees of the vertices. So I'm just going to write them right next to the letter. So at A, we only have 2 edges, so the degree of A is 2. D has 4 edges. C has 3. G has 3. F has 2. E has 3. And B has 5. Since we have 4 odd vertices, we cannot have an Euler circuit. Lastly, this diagram is connected. So again, let's go through and check the degrees of the vertices. A is 2, D is 4, C is 4, G is 4, F is 2, E is 4, and B is 6. Because we have all even vertices, we do have an Euler circuit. Okay, and it's connected. I'm not going to make you find the Euler circuit right now. We'll get to that in a few minutes. So that's the first theorem. The second theorem is the Euler path theorem. If a graph is connected and has exactly 2 odd vertices, then it has an Euler path. Typically, it has more than one Euler path. Any path must start and end at the odd vertices. So you start at one, you end at the other. If a graph has more than 2 odd vertices, it cannot have an Euler path. So let's look through these 3 graphs. We want to know if we have an Euler path, an Euler circuit, or neither. Our first graph is connected. And if we look at the degrees of the vertices, all of the vertices have a degree of 2. So since they are all even, we have a circuit. The second graph, again, is connected. If we look at all of the degrees of the vertices, we end up with 4 odd vertices, which means we do not have a path or a circuit. our last graph is connected. So let's go through the vertices. 2, 2, 3, 2, and 3. We have exactly 2 odd vertices, which means we have an Euler path. Okay, so let's go back and think back to the bridges of Königsberg, which we looked at in our previous video. So at the end of our last video, we took a map of the city of Königsberg and changed it into a graph, and this was our graph. So, is there an Euler circuit, an Euler path, or neither through the bridges of Königsberg? So if we look at the degrees of the vertices, we have 3, 3, 3, and 5. Well, we have more than 2 odd vertices, so there can be no Euler path or circuit through the bridges of Königsberg. So, Euler's circuit theorem talked about graphs with no odd vertices. Euler's path theorem talked about graphs with 2 or more odd vertices. What about graphs with 1 odd vertex? In Euler's sum of degrees theorem, he states that the sum of the degrees of all of the vertices of a graph is equal to twice the number of edges, and therefore an even number. So if you add up all of the degrees of the vertices, you always get an even number, and if you divide that number by 2, you get the number of edges. The second part of the theorem is a graph always has to have an even number of odd vertices, because the sum of the vertices has to be an even number. That means it is impossible to have an odd number of odd vertices. So you cannot have a graph with 1 odd vertex or 3 odd vertices or 5 odd vertices. Those are impossible. So let's go back and look at these 3 graphs again. We're going to look at the sum of the degrees, the number of edges, and the number of odd vertices. So we have already looked at the degrees of each of these vertices. We did that in example 2. If you add up all of these numbers, you get 8. So the sum of the vertices is 8. If we divide that by 2, 8 divided by 2 is 4, we get the number of edges, which we can confirm from the diagram. We have 1, 2, 3, 4. How many odd vertices do we have? 0. Let's look at the next one. If we add up the degrees, 3 plus 1 plus 1 plus 1 is 6. Divide it by 2, we get that there are 3 edges, which there are. There are 3 lines in this graph. And we have 4 odd vertices. Lastly, if we add up these degrees, 3 plus 3 is 6, plus 2 is 8, plus 2 is 10, plus 2 is 12. Divide by 2, we get the number of edges to be 6, which it is if you go through and count. We have 1, 2, 3, 4, 5, 6. And we have 2 odd vertices. So, in summary, the number of odd vertices, if you have 0 odd vertices, your graph has an Euler circuit. If you have 2 odd vertices, your graph has an Euler path. If you have 4, 6, 8, 10, 12, etc., your graph has neither an Euler circuit or an Euler path. And if you have 1, 3, 5, 7, 9, etc., odd vertices, that's impossible. So now that we've determined when there's an Euler path or when there's an Euler circuit, let's take a look at Flurry's algorithm. This gives us an idea of how to create those paths and circuits. So if you have a small graph, trial and error works. But real-life applications can have graphs with hundreds or thousands of vertices, so it's not practical to use trial and error. You're going to be there for days. So we have an algorithm. First, you need to make sure that your graph is connected and either has no odd vertices, which means you have a circuit, or has 2 odd vertices, which means you have a path. Choose a starting vertex. If your graph has an Euler circuit, you can choose any vertex. If your graph has an Euler path, you have to start at one of the odd vertices. As you travel through the graph, if you have a choice, do not cross a bridge of the yet to be traveled part of the graph. But if that's your only choice, then obviously you take it. If you remember from our last video, a bridge is an edge that, if removed, will disconnect the graph. And we'll see this in our example on the next slide. When you can't travel anymore, your circuit or path is complete. So for a circuit, that means you're back at the starting vertex. Or for a path, it means you have ended at the second odd vertex. So the basic idea of Flurry's algorithm is the bridges are the last edges that you should cross. So let's take a look at an example and see what this means. So here we have a diagram. I'm going to start in the top left box. And in each box we have 2 pictures. So this guy is starting at vertex F. Okay? So he is going to travel across this edge to C. So in the diagram on the left, that edge is getting erased so that we can help see what Flurry's algorithm says. So he is now at point C. None of the edges going out from point C are bridges, so he can take whichever path he chooses. So if we look in the second row, he happens to choose the path that takes him to D. So he has returned to D, so we've erased that path, or that edge. So if I look at this diagram here, he now has to make a choice. Does he go to A, to B, or to F? Well, this edge between D and F is now a bridge. If he crosses that edge, he has disconnected the graph because you're left with point F and the rest of the graph, and there's no way to get back to the rest of the path that he needs to walk. So he cannot take that edge. So instead, he decides to go to A. So now, at vertex A, he again has a choice. He can either continue to C or go around to E, or he could go to B. Well, if he chooses to go to B, again, that is a bridge. He has disconnected the graph. There are now 2 separate pieces, so he cannot take that route. So if we continue, he decides to go to vertex C. And now he has no more choices. He can only take the path in front of him because I could unfold this graph into a straight line. So he's going to continue to walk to E, then around to A, then to B, then to D, and then back to F, where he started. So Flurry's algorithm is basically just common sense. Like here, don't walk from A to B, otherwise you have no way to finish up this part of the graph. Here, don't walk from D to F or you're back where you started and you've missed a huge chunk of the graph. So, let's try this on our own. Let's apply Flurry's algorithm to this graph. So, the first thing we have to determine is, can we make an Euler circuit or an Euler path? So we need to look at the degrees of the vertices. Well, we do have two odd vertices, which means we have to start at one odd vertex and end at the other. I choose to start at this one and end at this one. So I'm going to go ahead and start making my path. I choose to go this way first, then here, and here. I'm forced to go back around here. So far, I haven't had a situation where I've encountered a bridge. I'm going to keep going. I'm going to go this way. Then let me go back this way. Okay, well, there's my Euler path. Let's try another example. Again, before we can start, we need to look and see, do we have an Euler path or an Euler circuit? So I'm going to go through the degrees of each of these vertices. Okay. Again, with this one, I have two odd vertices. I'm going to choose to start at E and end at J. So, let me start by going this direction. I'll come back here. And then I'm going to go over here. All right. I've completed my Euler path. Now, because this graph is symmetrical, you're less likely to encounter a bridge. The graph that we looked at originally, because it was not symmetrical at all, there were definitely bridges as we went through our path. Let's look at one more concept. We want to look at Eulerizing a graph. So, in the previous video, we mentioned some applications, like delivering the mail, delivering pizzas, things that use graphs and can be rewritten as graphs. Ultimately, the goal is to find optimal exhaustive routes. This is a route that travels along the edge of a graph and passes through every edge at least once. This could be an Euler circuit if there are no odd vertices, or an Euler path if there are 2 odd vertices. But for graphs with more than 2 odd vertices, an exhaustive route will require recrossing some of the edges. Your goal is to find an exhaustive route that recrosses the fewest number of edges. Why is that? Well, because in most of these real-life applications, each edge that you travel across represents an additional cost. The more edges in the route, the more expensive the route is. Like if you're looking at an Amazon truck, if they have to retrace their steps, they are spending more money in gas and they are spending more time, so they have to pay their driver more money because he's working more hours. Every time they retrace their steps, it costs money. So, in an exhaustive route, the first pass along an edge is a necessary cost. Any additional pass along an edge is a wasted cost. So, an exhaustive route that minimizes cost would be your optimal exhaustive route. It's the one with the fewest number of wasted expenses. We have a few rules though. You can turn an odd vertex into an even vertex by adding a duplicate edge in a strategic place. So this process of adding extra edges is called Eulerizing a graph. So, if I am Eulerizing a graph to make an Euler circuit, I need all of the vertices to be even vertices. So, first I have to find the odd vertices. Then I need to create parallel edges until all of my vertices are even, and then I can make my circuit. Right now, we're not going to worry about finding the Euler circuit. We just want to Eulerize the graph. So make sure that all of the vertices are even. So in my first graph, I'm going to go through and look at the degree of each vertex. So you can see my odd vertices here. So I need to add some extra parallel edges to make all of these even vertices. Well, if I just connect these two, now they both have a degree of 4. And I can do the same on each of the sides. So now, all of those odd vertices are now even vertices. So I have Eulerized my graph. But let's look at another example. If I go through and write the degrees for each of my vertices, I have a similar setup as my first graph, but I do have some more odd vertices because I have a bigger graph. So, again, I need to connect some of these odd vertices so that they are all even. So I'm going to start doing what I did on the previous graph. I'm going to add an edge there. Now both of these are 4s. This vertex does not have another odd vertex adjacent to it. You might think, well, you can just do this. No. If you think about this as a neighborhood that an Amazon truck is traveling down, if you try to connect these two, you just drove through someone's house. You can't do that. You can only go along the edges that are already there. So maybe I go here and then here. Now this vertex is a 4, this one is a 4, and this one is a 4. So that works. Here I can just connect those two, and now they are 4s. Here I can connect those two to be 4s. Again, I run into the same problem that I had over here. So I'm going to go to the corner and then go around, and now all of these are 4s. And then I can connect these two. So now I have a graph where all of my vertices are even. So I have Eulerized that graph. Now, there is a variation on this. Sometimes you need an exhaustive route, but it doesn't matter if it starts and ends in the same place. For example, a parade route. Parades usually don't start and end in the same place, but maybe you want to go down all the neighborhood streets. So, we're going to use the same process, except we want to leave 2 odd vertices. So, let's start looking at the first one. These are the same graphs that we did in the last example, so we already know what all of these degrees are. Now, I need to connect some of these odd vertices to make them even, but I'm okay with still leaving 2 odd vertices. And I will tell you, there is an efficient way and an inefficient way to do this. First, I'm going to show you the inefficient way. This is the more expensive way to do this. Well, if I say, well, I'm going to connect these 2, connect these 2, connect these 2, and I'm left with 2 odd ones. Well, I added 1, 2, 3, 4, 5, 6 extra edges. I can do better than that and save myself some money. If I connect these 2 edges, connect these 2 edges, connect these 2 edges, now these are all 4s. And I still have my 2 odd vertices. And in this case, I only added 3 extra edges. That's a whole lot better than the previous example where I added 6 edges. Now, a trick is, if you already found an Eulerization, just delete an edge, or maybe multiple edges, so that you still have 2 odd vertices. Don't change what you already got to work. Let's look at the bigger graph. Okay, so again, got my odd vertices, and I need to connect them so that I make most of them into even vertices, but leave 2 of them as odd vertices. I'm going to go back to the previous slide and look at how we Eulerized our graph. Basically, I'm going to do the same thing I did here, except I'm going to leave 2 of these odd vertices disconnected. So, which would be cheaper? To delete this edge and make these 2 my odd vertices, or to delete both of these edges and make these 2 my odd vertices? Well, clearly the second one. You want the fewest extra edges possible. So that's what I'm going to do. For my semi-Eulerization, I make all of these 4s. And I leave these 2 as my odd vertices. Here I've added 1, 2, 3, 4, 5, 6 extra edges. So that's it. We have our 3 theorems telling us when we have an Euler path or an Euler circuit, and the sum of degrees theorem, which says you have to have an even number of odd vertices. We have Flurry's algorithm to give us some guidance when trying to find an Euler path or an Euler circuit. And we have a process for Eulerization and semi-Eulerization.